Hey everyone. Lesson 3 we're going to look at today, and that is exponential functions. So the graphs of exponential functions, essentially. This first page is really good, but if I was to do every single thing on this lesson, it would probably be like 3 videos, 15 minutes each. So I'm going to jump around here and there, but this is an example of a real-life exponential growth situation where bacteria is essentially doubling every hour. Okay, so it's growing. And then an exponential decay example would be Chernobyl with the nuclear accident, and radioactive material was spilled, and the amount of radioactivity units left in the atmosphere after 1 week, 2 weeks, 3 weeks was basically half of what it was the week before. So those are an example of exponential growth in which it grows and decay. So we're going to look at the next page now and talk about what the exponential function looks like. And this is essentially what the graph looks like. Y equals a times b to the x. Okay, and we'll talk about how a affects a graph and how b affects a graph and all the scoop with that. But just to note here, b, if it's an exponential function, has to be greater than 0 and it can't equal 1. Okay, so it could be a fraction between 0 and 1 or some whole number or fraction greater than 1. Okay, we're going to look at the graphs of 2 to the x and 1/2 to the x just to see in general what these graphs look like. Okay, state the values of a and b for each of these. Well, a is the number in front of that, so that would just be 1, whereas b is your base of your power, which would be 2. For this one, a is 1 again because the number in front is a 1, but the base of our power is 1/2. Okay, sketch the graph. So what we're going to do is we're going to come up with the y values here by subbing into this equation. So if you sub x, each one of these x values in there, you can fill in this table. So, and on these ones here, you could math fraction it if you like, which for the negative exponents. Okay, so why don't you guys go ahead and fill in that table and go ahead and do this one as well, and then plot the points on the graph and we'll see what we get, okay? So fill in this table, plot the graph for each one. All right, and then we'll check back. So pause your video now. Okay, so check your numbers in the tables. Hopefully you have the same thing as I do, and your graph should look like this. So y equals 2 to the x, because it's increasing as we move to the right, this would be an example of a growth function. Okay, and this red graph, because we're decreasing as we go to the right, that would be an example of a decay exponential function. Okay, and you'll notice the nature of the bases as a result of that. So when the base is greater than 1, like 2, 3, 5 halves, right? You're going to have a growth function, and if it's between 0 and 1, your base, 0, like 1/2, you would have a decay function. It would decrease as x increases, okay? Now for both of these, you'll notice that they didn't cross the x-axis, nor would they, because it's like 1 over, and it would just keep being 1 over a really big number. So as a result, we have what's called a horizontal asymptote at y equals 0. Okay, so they talk about that here. An asymptote is a line whose distance from a given curve gets closer and closer to 0. So as we moved further this way on the red line, it got closer to 0, but it would not cross. Okay, so we're going to fill in the rest of these, the domain, the range, for each of those graphs, what the x-intercept, y-intercept, and equation of the asymptotes are. And I'll give you a little hint. Very much everything is the same. Okay, and then you can fill in the growth and decay, which we already know because I gave to you. So please fill in the table, pause your video, do part D and E essentially. Okay, so we should have gotten these values. Noticed they were really, as far as domain range, all the intercepts and the asymptotes, these graphs appear to be very similar. So the domain, it goes forever left and right, so element of the reals. And I also wrote the interval notation way of writing that. So if it's element of the reals, that's basically like saying from negative infinity to infinity. So this is not an ordered pair that I'm writing here. This is the interval notation of domain. Okay, and range, y is greater than 0, can't equal 0, okay, because it didn't cross the x-axis. Or, written in interval notation, that would be 0, not including 0, so round bracket, comma, infinity. And infinity is never included with interval notation because infinity isn't really a number, so you can't include it. It's just an idea. X-intercept of a graph, well, it doesn't cross the x-axis, so therefore none. Y-intercept of the graph, they both crossed at y equals 1. The asymptote was the x-axis, which has an equation of y equals 0. 2 to the x is a growth, and 1/2 to the x is an example of a decay function. All right, let's look at the next page. Okay, I'm just going to run through this quickly with you. We're not doing the full-on thing. The purpose of this lesson is by comparing, if you have a larger base, what the graph looks like. And essentially, y equals 3 to the x, we'd have something like that. Y equals 10 to the x, so that might be 3 to the x. Y equals 10 to the x would be steeper, okay? And as the base on your power increases, it gets steeper. And the reciprocal of those, as we discovered with the last page, are just the same but a reflection in the y-axis. So this would be y equals 1/10 to the x and y equals 1/3 to the x. Okay, so to fill in part B, the value of b affects the steepness of the graph as x increases. Complete the following. When b is greater than 1, the curve rises more sharply as b increases. That's these two graphs. Okay, if b is between 0 and 1, the curve, these ones were falling, so falls more steeply, if that's more sharply, I should say. All right, so I think that's all we're going to do on this page. Let's take a look at the next one. Again, this page would be good to do because we're a little short on time, I'm going to kind of gloss over it. This exploration is looking at what this value of a does to the graph. Well, in essence, what that does is if we look at the y-intercept, a is really your y-intercept is what it comes down to. And the reason why is if you put x to 0, right? So set x to 0 once the y-intercept, you would have 3 to the 0, so that y-intercept is 1, like our basic graphs. This one, again, this would be 2 times 3 to the 0, so our y-intercept would be 2. Same thing here, y-intercept of 5, y-intercept of 0.5. Okay, so in essence, essentially that a value is the y-intercept. Now if it was negative, what would happen is it would reflect over the axes and it would still be our y-intercept, but yeah, okay, let's look at the next page. Okay, we're going to summarize those characteristics we were just talking about. So our basic exponential graph looks like this. Okay, crosses the y-axis at 1. It has a horizontal asymptote of y equals 0. Okay, and domain and range we talked about already, so let's fill this in. Y-intercept is, I guess if you wanted to go with this actual equation, the y-intercept would be a. Okay, so and if it was just a basic graph like y equals 2 to the x, it would equal 1. Okay, there is no x-intercept. The x-axis is a horizontal asymptote. That's a weird word to spell. Okay, the domain, it goes forever left and right, so domain is element of the reals, xer, or in interval notation, negative infinity to infinity. The range looks like we're greater than 0, or written in interval notation, that would be 0 to, we're getting really sloppy here, 0 to infinity. Okay, if a is greater than 0, so the y-intercept positive, right? And b is greater than 1, which means it would be a growth function. Oh, sorry, gave that one away. Represents a growth function. When b is between 0 and 1, it's a decay function. And the value of b affects the steepness. B greater than 1, the curve rises sharply as b increases, and other way around, falls. Value of a affects the vertical stretch of the graph. Choose the correct alternative. When a is greater than 1, the stretch is an expansion. It gets bigger, basically. If it's between 0 and 1, the stretch is a compression. Your y-intercept would get smaller. And if a is less than 0, there is a reflection in the x-axis. Okay, so it would look like that, and then we'd reflect. All right, good. Describe how the graph, so this is really just transformations question. Describe how the graph of the second function compares to the graph of the first function. All right, so what you do is compare what is different. Okay, we've got things happening to the x. We've got something in front, and this was a 1 in front before. The 4 doesn't change, and it won't. You won't be given a question necessarily where that happens. So think transformations. Sort it out. So any stretches? Yes, we have a 2 in front, so that's going to be a vertical stretch by a factor of 2. I'm just going to abbreviate this if you don't mind. Okay, reflections. Were there any negatives in front of y or x? Nope, so no reflections. Translations, adding or subtracting to y or x? Yes, x was replaced with x minus 2, so that would be moving right 2. Okay, so there's our transformations. Why don't you guys try B, and then we'll go over it in a second. So pause your video, please. Okay, I thought you might get a little stuck on this one. So I rewrote the equation, brought that 4 over, and also x over 5 is the same as having 1/5 times x, okay? Because 1/5 times x over 1, that would end up being x over 5 times 1, 5. Okay, so just kind of writing that in a different way so you can see what the b value is or what is being multiplied by x. So pause your video again and try that one again and see if you can get your transformations now the way it's written. Okay. All right. Okay, so horizontal stretch by a factor of 5. So there's a number of 1/5 in front of x, so you reciprocal that to get your stretch factor of 5. There's a negative in front of the whole function, so that's going to reflect it over the x-axis. And then finally, there's either a +4 with the y, which means opposite, so it would move not up 4 but down 4, or you could move that over and then it's -4 and therefore it's moved down 4. And again, notice we have it in the order stretch, reflect, translate. Okay, so example 2, explain using transformations why the graph of y equals 1/3 to the x is a reflection in the y-axis of the graph of y equals 3 to the x. Okay, so think about how we could write this differently. Okay, y equals 1/3 to the x. Could I write that as y equals 3 to some exponent? Think 1/3, that's like 1 over 3 to the 1. If we bring that up to the top, we could write that as 3 to the -1, and then the x is still outside the brackets, so then that would become 3 to the -x. Okay, so if you compare to the original graph, x was basically replaced with -x here. So think transformations when x is replaced with -x. That is a reflection over the, think about on the graph, x goes negative, so over the y-axis. Good. Okay, let's look at the last example on the next page. Okay, so consider the function f of x equals 4 to the x plus 2 minus 6. Okay, without using the graphing calculator, determine the domain and the range of the function. Okay, so why are they making you do this? Because you'll have a calculator. It's because, you know, on the diploma or possibly a unit test, instead of having, you know, the 2 and the 6 as numbers, they could be variables, and then you wouldn't be able to use your graphing calculator. So you have to know how to do it. All right, so the basic graph of an exponential function looks like that, right? Horizontal asymptote of y equals 0. So if we figure out what transformations have been done, so let's just do that a minute. X was replaced with x plus 2, so from the basic y equals 4 to the x graph, which would probably look like this. Okay, so that means it moved left 2 and down 6. Okay, so if we move this graph left 2, not a lot's going to happen. It's just going to kind of look like that, right? Maybe the y-intercept changes, right? But if we move it down 6, this horizontal asymptote moves down 6. So that would now be at y equals -6, which means our graph would look like this. Okay, so this would be y equals 4 to the x plus 2, and then -6. Okay, so let's figure this out now, domain and range. So domain would still be element in the reals, keeps going forever left and right. The only thing you could do to make the domain different is do the inverse function, which we will look at later. Range, y is now greater than -6 because we moved down 6. Y-intercept, well, it's pretty hard to tell from here because we also moved left 2, so it's not a matter of just going a y-intercept of 1 down 6. So how do we find a y-intercept? We set x to 0. So take your function y equals 4 to the, and put 0 in for x. So 0 plus 2 minus 6. And we would get, pause your video and figure that out. Okay, so I got 10, but I didn't make a mistake, so I think that this graph is steeper than I thought. Okay, any asymptotes? Well, as you could tell, we moved down 6, so our horizontal asymptote is y equals -6. Okay, so graph is a little bit steeper, that's why we got a y-intercept of 10. Check it on the calculator, see if we did it right, but it should be good. All right, we'll see you on the next time.